Welcome to the second episode of Navigating Metric Space Topology. Now, before we get started, I quickly want to spend a few minutes talking about some logistical details for the series. The very first thing is that this series is going to be a pretty abstract series. It's going to be a proof-based introduction. And what is it an introduction to? Well, it's an introduction to basics of metric space topology. And we are only going to cover really the minimum, very foundational material that you absolutely have to know. Namely, we're going to cover things like Euclidean topology, and we're going to cover things like compactness and connectedness. I'm not super sure how long this is going to take. I really do want to get it within 5 videos, but I think that's too much to hope for. So I'm guessing it's going to take anywhere between 5 to 10 videos. And each video is not going to be too long. If you think about a college lecture, it's probably going to be an hour to 15 minutes. These videos are going to be much shorter than that per video. So this is not going to take too much of your time away. And an important thing to be pointed out is what is a prerequisite. And now this is pretty debatable, but I'm not entirely incorrect to say the prerequisite is just high school mathematics. In the sense that we're not really going to use any of the college level mathematics that's really required. I think if you know calculus, that might be helpful, but the reason that this is not entirely accurate is because, let's say for a really hard expository writing class in college, maybe all they say is that the prerequisite is high school English class, but that doesn't mean the class is not going to be challenging. So the same thing applies here. The prerequisite is pretty low, but the class itself, the content is going to be pretty challenging. This is going to be much harder than, say, Calculus 1, 2, or 3, much harder. And now the final thing I want to emphasize are the problems. So for every episode, I will include in the description a link to some problems that go along with the episode. And I really highly encourage you to try just at least one problem per episode. This is not going to take too much of your time, and it's absolutely going to be very beneficial. So I really highly encourage you to do so. And the second thing is I really encourage you to comment solutions to the problems below. So when I say a solution, it's probably going to be a proof of some statement or counterexample. And if you commented, I can try to respond to some of them, or other people in the channel can try to give you some answer to your solution to see if the proof is correct or well written. And I really encourage you to do so. Anyway, I think that's all I want to say for now. Let's get on to the second episode. In this episode, we're gonna start by introducing one of the main protagonists of this entire series, which is the set of real numbers. Now, even before we talk about R, let's cover some of the basics first. The set of numbers that we're really going to take for granted in this episode are things like the set of integers. So set of integers is a set consisting of elements 0, 1, 2, 3, and also -1, -2, -3, and so on, extending out both directions to infinity. So this is the set of integers. And in addition to this, you may also know the set of rational numbers, so which is often denoted Q. And Q consists of all numbers of the form a divided by b, where a and b are integers. And I guess we cannot divide by 0, so we will add in the condition b not equals to 0. So for example, something like 5/2, which is an integer divided by an integer, this would be a rational number, and we denote it as follows. What this means is that 5/2 is an element of Q. It belongs to the set of rational numbers. And for example, 0.1 repeating, which is 1/9, this would be also an element of Q because it can be written as integer divided by integer. And it's pretty easy to see that every integer is a rational number because, for example, -2 is -2 divided by 1. So that certainly belongs to the set of rational numbers. So a way of writing that is that the set of integers is a subset of the set of rational numbers. So what this sign is saying is that for each element of integer, that is also an element of the set of rational numbers. Now, in this series, we are going to take the set of integers, the set of rational numbers, really as granted. Any property of integers or rational numbers, like, for example, multiplication is commutative, associative for rational numbers, these kind of properties that we're familiar with from high school, we will assume them. We will not worry about going too low level, too much down to foundation to actually prove or construct what integers and rational numbers actually are. Having said that, now let's talk about the set of real numbers. What is R? Now this actually turns out to be a really hard question. R is really notoriously hard to define precisely. And let me give you some of the incorrect definitions that might go through your mind. So here's one attempt. You may say R is the set consisting of rational numbers and also irrational numbers. Now here you might be familiar with the fact that not every number that you might care about is rational. For example, perhaps the simplest example is log base 2 of 3. Given that you have defined this precisely somehow, I claim that this is not rational. So what I'm saying is, if you write this as a divided by b, where a and b are integers, something goes wrong. This is impossible. And the reason is, well, I mean, given that you know what this is, you probably know this better be positive. So we can assume a and b are actually positive integers, a and b are greater than 0. And given that, we can rewrite this. This exactly means 2 raised to a over b power is 3, but this implies 2 raised to a is equal to 3 raised to b power by raising both sides to b. And we see, because a and b are positive integers, that this is an even number, whereas this number, gained by multiplying 3 to itself many times, this must be odd. And obviously this cannot happen, so we get a contradiction. So we cannot have that log base 2 of 3 is rational. So if you know existence of supposedly numbers that are not rational, you might try to go for a definition of R that is a rational number and irrational number. But this makes no sense. This makes absolutely no sense, because now you are in a position where you have to define what an irrational number is. So if you're defining R as rational plus irrational, then you better have defined irrational number first. But what is this? Are we gonna define it as a number that's not rational? Well, now we have to define what a number is, and defining what a number is sounds really harder than defining what a real number is. After all, what is a number? Is number something we can count with our hands, like 1, 2, 3, 4, 5? Is a number a complex number? Is a number quaternion, or is it something else? Defining number precisely, this is already a pretty hard task. And really, how irrational number really should be defined, so a correct definition of irrational number is to define real numbers first. So define this first, and then define irrational number to be a real number that is not rational. So to avoid the circular reasoning here, we need a definition of real numbers first. So this first definition is not going to work. Now here, I should also point out that defining log base 2 of 3, this is also not an easy task. Because what is log base 2 of 3? Well, this is a real number, x, such that when I raise 2 to x power, you get 3. So in order to define log base 2 of 3, we first need to define what a real number is. So we absolutely need this. And we also need to define what it means to raise 2 to a real number. For example, it's easy enough to define like 2 to the 5th. You just define that to be 2 multiplied to itself 5 times. But what is 2 raised to, say, pi? Like how do we define this? It's not obvious at all. And then there is a third problem. So there is a third problem with defining log base 2 of 3 is that why does log base 2 of 3 have to exist? Those log base 2 of 3 exist. So once I define log base 2 of 3 as a real number, such that 2 raised to x power is 3, how do you know there is a real number satisfying this? So there are many problems with even defining log base 2 of 3, even though it can all be done, and it turns out there is a real number log base 2 of 3, so this is a well-defined concept, but this takes time. So this first definition of real numbers didn't quite work out. Here is a second attempt. So the second attempt might be, maybe it's all the numbers, maybe real numbers is everything on the real line. So you might have this picture from, say, high school, where we have this number line with 0, -1, 2, -1, -2. So you have all of these numbers on it, and maybe real number is everything here. So maybe this is x-axis on the xy plane, and you define real numbers to be this line. But again, this makes no sense, because what is this number line? Well, this is a pictorial depiction of real numbers. So even to define what this line really is or represents, you need to define real numbers before. Otherwise, it's a circular reasoning. So even the second definition certainly doesn't work out, but at least it provides some intuition towards the correct definition. And what do I mean by this? Well, let's assume for the moment that we defined the real numbers somehow correctly, and we defined log base 2 of 3 correctly, and we know it actually exists. So we have log base 2 of 3 somewhere on this number line, so around here. Once everything is properly defined, you can show this is approximately 1.5849625 and so on. And now consider the following set. Let's consider all the rational numbers, so set of rational numbers, such that it's less than or equal to log base 2 of 3. So if I depict this on the number line, so I'm thinking of all the rational numbers that's less than this dot. So obviously I'm not really including every point on the number line, I'm only including the rational numbers, but pictorially you can imagine it stretches towards negative infinity like this. Obviously, we're gonna leave out a lot of irrational numbers in between, but hopefully you get the point. And now we know this log base 2 of 3 is not rational. So when I say less than or equal to here, well, I mean equality can't happen. So this is really a strict inequality. So in the depiction, if I give this set a name A, say, A really looks something like this. We're gonna exclude this dot, this log base 2 of 3, and we're gonna pick up all the rational numbers to the left of it. And now one observation we are going to make is that A has an upper bound in Q. So what do I mean by an upper bound in Q? Well, I simply mean a number M, that's a rational number, such that if I look at any element of A, so here this is a for all sign, so no matter what element I pick in A, we have that A is less than or equal to M. So this would be a definition of an upper bound. So for example, if I consider 3 on this real line, and if I let this be M, then this is certainly an upper bound of A in Q, because M is a rational number, and we see that all the elements of A is less than or equal to this capital M. But surely we can do better. We can do better than this capital M in the sense that we can find a smaller upper bound. So for example, because log base 2 of 3 is 1.58496 and so on, surely we can shrink M. We can let M be 2, and this is still an upper bound in Q. But of course we can do better. We can make M even smaller. So say M equals to 1.59. This is certainly a rational number because we can write it as 159 divided by 100, integer divided by integer. So it's a rational number, and it's certainly larger than log base 2 of 3. So we see that this is still an upper bound of A in Q. And we can clearly do better. We can shrink it to 1.585, say, and that would still be an upper bound. And it should be pretty clear because, and this is the key thing, because this is irrational, this number is not in Q, we can always improve M, but we cannot find the optimal M in Q. So here the key observation is that A does not have the least upper bound in Q. So the least upper bound in Q is exactly what it reads like. It's an upper bound in Q that also happens to be the smallest possible upper bound. And here again, the problem is that the smallest possible upper bound really looks like log base 2 of 3. So it looks like this is the least upper bound, but the problem is this is not an upper bound in Q because it's not in Q. Remember that upper bound in Q has to be a rational number. But surely, and this is the key thing, if I change it to an upper bound in R, so an upper bound in R is now going to allow any real number to be an upper bound. So instead of Q, we're going to allow any real number, and now A indeed has the least upper bound in R, and that would exactly be this log base 2 of 3. And this is really the key distinction that we're going to make between the real numbers and rational numbers. In rational numbers, it's possible for us to have an upper bound, but not have a least upper bound. But in real numbers, intuitively the fact that we have the entire line and we have numbers like log base 2 of 3 actually in it should allow us to always find the least upper bound. So this is a really key intuition that we're gonna talk more about very soon. But before we do so, let me mention one more incorrect definition of real numbers. So here is an attempt number 3, and this one is actually not entirely a failure, and a way of going about it is to say real numbers is all possible decimal expansions. So for example, you may say 3.14159. So if I just continue the decimal expansion infinitely, so numbers we get of this form, all of these are exactly the real numbers. So maybe this is how you define R. And something to be pointed out, I'm not gonna prove it here, but it's not too hard to show that if a decimal expansion repeats, so for example, if I have something like 0.787878 and so on, so you have this repeating decimal expansion, this happens if and only if the real number is rational. So when I say if and only if, so this is a sign for if and only if, let me just point out for those of you that have not encountered this rigorously, that I really mean two things. I mean if, in the sense that if real number is rational, then the decimal expansion of the real number is actually going to repeat, and only if, in the sense that if the decimal expansion repeats, then the real number happens to be rational. These are two distinct implications, and you do have to be careful of this in mathematics. So I'm here assuming that both the forward implication and the backwards implication are true. So just keep that in mind. And this is a fact that can be shown. I will not digress and do it right now. So what you might think is that if we not only include the repeating decimal expansion, but we also include decimal expansions that has no repeating digits. So if we consider something like decimal expansion of pi, say, of course pi also is kind of hard to define rigorously, but anyway, given that, you might say maybe this is the real numbers. And this is actually a pretty good idea, and I'd say it's like even halfway there, but this still needs a lot more work to make it a good definition of R. And here are some problems with this definition. So here are some reasons that I'm going to cross it out. And one reason is that it's not clear how unique a decimal expansion is. So for example, you may know of this famous ambiguity that if I have 0.9 repeating, this actually happens to be the same as 1.0 repeating, or just 1. And you can devise similar examples, like for example, if you have 0.19 repeating, this is actually same as 0.20 repeating, and so on. So there's some ambiguity on how unique a decimal expansion is. And a natural question to ask is, are there any other exception? So here, one exception is when I have 9 repeating, you can replace that with 0 repeating and just increase the digit of the previous one by 1. Do we have any other exceptions to the uniqueness of the decimal expansion? So you need to address this. But perhaps a harder problem is that it's not clear from the get-go that this definition allows R to be an ordered field. So we want R to be an ordered field, and I'm not going to define this term precisely in this video, but just to give you some intuition, a field means that you have the arithmetic operations with some nice properties. So field means we have things like multiplication, we have division by non-zero elements, addition, subtraction, and these satisfy nice properties, like for example the distributive property for plus and times. And the ordered part, I'm not gonna define this precisely right now also, but this means if I have two real numbers, we can compare them with things like less than or equal to, greater than or equal to, less than, so there's the notional comparison, and this also satisfies some nice axioms, but I'm not gonna make everything precise right now. And the point is, if I just define real numbers to be decimal expansion, you also have to tell me how do you make it into an ordered field, because you really want to be able to add real numbers or multiply real numbers. If I just define it as decimal expansions that do not repeat, how do you define multiplication of two such numbers? So if I give you two decimal expansions, not repeating perhaps, how do you define multiplication, division, and things like this? Is this an obvious thing to define for decimal expansion? And in addition to that, you of course have to grapple with the fact that you have to justify why this definition is allowing you to do more things than you can do with the rational numbers. So for example, rational numbers, certainly you have all of these arithmetic operations, you have the notional comparison in Q. What additional properties are we gaining by allowing the decimal expansions that do not repeat? So you also have to you also have to think about things like that. But let me add here that once you do define real numbers correctly, whatever correctly means, then every real number does have a decimal expansion, and the only ambiguity in the uniqueness of decimal expansion is the one that I illustrated here. Only ambiguity, only time decimal expansion is not unique, is when we have repeating 9s or repeating 0s. So anyway, we talked a lot about what are the incorrect definitions of R. What is a correct definition? And I'm going to disappoint you a little bit. I'm actually not going to give you the correct definition in this video. What we're going to do in this series is to use what's the following definition, which is like 90% correct definition. So this is an almost correct definition of real numbers, and this should suffice for the series. If I ever do a series on real analysis, I can do a really precise definition there. But the definition that we are going to use in this series is that real numbers is R that we know from high school. So I wrote real numbers with high school intuition. So here when I say high school intuition, I mean real numbers have natural things like it has decimal expansion, whose uniqueness I mentioned before. You have things like addition, multiplication of real numbers. You have nice properties like distributive property. You have that addition is commutative, multiplication is commutative, associative. So you have things like that. So you have this nice high school intuition. So all of this is going to carry through. But plus, and this is the important thing, real numbers definitionally is going to have what's called a least upper bound property. So what is a least upper bound property? Well, what I mean is that if I ever have a subset of real numbers, so if I have a subset of R, and this is, say, non-empty, so it has at least one element, and let's say it has an upper bound. So when I say upper bound here, I always mean upper bound in the real numbers, so upper bound in R. Then what least upper bound property says is that A actually has the least upper bound. So remember that example from a while ago where I considered the rational numbers less than log base 2 of 3, and in that case we do have the least upper bound in R, which happen to be log base 2 of 3. So as long as you have an upper bound, unlike the rational numbers, we actually should have the least upper bound in R. This least upper bound property is really the key definition, a key part in the definition of real numbers that we are going to be utilizing throughout the series. Now, I do point out that least upper bound is often also called a supremum, and you will see the least upper bound of A often written as supremum of A, like this. Just so you have some intuition over supremum, let's quickly do one example. Let's say our A is of the following form. Let's say it's all elements of the form 1 minus 1 over n, where n is a positive integer. So if we consider the real line, and let's say we have 0 here and we have 1 here, the elements of A are going to be the following. We have 1 minus 1 over 1, which is 0. Then we have 1 minus 1 half when n is 2, so we have 1 half. Then we have 1 minus 1 third, so that's 1 minus 1 third. So you go 1, then you go back 1 third. So that's going to be this point. Then you're going to have 1 minus 1 fourth, and so on. So what we get is we get this series of dots, the series of points in A that seems to be getting closer and closer to 1. And in this case, what would be the supremum of A? So what's the least upper bound? Well, what are some examples of upper bound of A? Well, for example, this point is an upper bound. It's greater than or equal to anything in A. And this is an upper bound, but it's a smaller one. And the smallest possible one, which we know has to exist by the least upper bound property, is clearly 1. So I claim that supremum of A is 1. You cannot get smaller than 1. And to see this, realize that 1 is certainly an upper bound of A, because all elements of A, in fact, is smaller than 1, just by definition. And if we go even a tiny bit smaller than 1, so if we go a tiny bit smaller than 1, and we pick our upper bound to be somewhere here, so even if we move a really small positive distance from 1, then we claim that this is no longer an upper bound. You can find elements of A, a green dot, in the region to the right. And to really prove this rigorously, to actually justify the fact that there exist green dots to the right of it, we really need to show the following. We want to show that no matter what epsilon greater than 0 you give me, so epsilon here is a real number, and no matter how small it is, as long as it's positive, we really want to show that there exists some n, and whenever I use capital N in the series, it's going to stand for some positive integer, such that 1 over n is smaller than epsilon. And this exactly means that no matter how small a positive number is, this 1 over n can be made smaller than that number, which means this 1 minus 1 over n will be as close to, it can be as close to 1 as we want. And that's going to justify the fact that if we go back a distance of epsilon, then that cannot be an upper bound. Now, proving this rigorously is actually surprisingly slightly annoying. You can actually do it using the least upper bound property and exact definition of real numbers, but since we are allowing for some high school intuition, I guess the easiest way of doing this is to realize that this epsilon has a decimal expansion. It's a positive real number, so we know it has some decimal expansion. Maybe it's like 0.01, or it can really be anything. And now just check. If you know how to divide 1 by a positive integer and get its decimal expansion, just realize that for large enough n, certainly the decimal expansion we get here is going to be smaller than 0.01. So that would be, assuming some facts about decimal expansion, that would be the easiest way of getting this. To proceed, let me quickly mention 2 facts related to Supremum that you probably want to know. The first one is that if maximum of A exists, so if this exists, then Supremum of A is also A. So what is a maximum of A exactly? Well, a maximum of A, this is an element of A that also happens to be an upper bound of A. In other words, it's an element of A that's actually greater than or equal to anything in A. So in this case, it's easy to see that Supremum is in fact the same as maximum. Now it's important to point out, even in the case of real numbers or subsets of real numbers, maximum doesn't have to exist. So for example, in this case, realize that A does not have maximum. Maximum of A does not exist. Remember, A was the sequence of green dots here, and the sequence of green dots were always getting larger and larger, strictly larger and larger. So there does not exist a single element of A that's larger than everything else in A, but it of course has a supremum, which is 1, which does not happen to lie in A. So 1 here is not a maximum, but it is a supremum. Now the second point I want to make is that the real numbers actually also has what's called the greatest lower bound property. And this is analogous to the least upper bound property. What we really mean is that if you have a subset of R that's non-empty, and we happen to have a lower bound of it, then it turns out it also has the greatest lower bound. It has a lower bound that's the largest possible. And the greatest lower bound is often also called infimum, and it's often denoted infimum of the set, say A. It turns out that the greatest lower bound property can really be deduced from the least upper bound property. One way of seeing this is to, if you're working with set A, negate all elements of A. So for each element of A, consider its negative to form another set. And now it's not too hard to see that the notion of lower bound and upper bound and the notion of infimum and supremum are going to be switched. And that's going to allow you to deduce this. And I'll leave it as an exercise for you to rigorously write this out. Before we wrap up, I want to quickly talk about one more property of the real numbers that really distinguishes it from the rational numbers, and it is that the real numbers is uncountable. To define uncountable, let me first introduce the notion of a sequence, which you probably already intuitively know. So if I say a sequence in some set, so let's say set A, all I mean is an association for each positive integer. So if I consider 1, 2, 3, 4, and so on, I associate to each positive integer an element of A. So I have some A sub 1, which is an element of A. I have A sub 2, which is an element of A, and so on, one for each positive integer. You can, of course, have duplicates. So a sequence like 1, 1, 1, 1, this is a valid sequence. That's okay. But once the notion of sequence is defined, what we can say is that A is countable if there is a sequence containing all of the elements of A. So if I have a sequence, say sequence in A, that has all elements of A, say possibly with repeats, so you can list an element of A more than once. If this is true, then we say A is countable. And the reason it's called countable is easy enough. If I can list every element of A as a sequence, then we can count it. You have the first element, we have the second element, and so on. Let's look at some examples. So if we look at the set of integers, I claim that z is countable. So how do I list every element of integers in a sequence? So first element, second element, and so on. Well, here is one easy way. Start with 0, and then do 1 minus 1, 2 minus 2, 3 minus 3, and just continue this. So we have this being a sub 1, a sub 2, a sub 3, and so on. And it's clear that every element of integer is going to be contained in this sequence. So this is good. Now let's try something much harder. Let's try Q. Is Q countable? I claim that the answer is yes. We can actually list all elements of Q, and this might seem a bit daunting. How do you list every integer divided by integer in this one-dimensional sequence? And here is a trick. First, let's just look at positive rationals. So if you consider positive rational, we have 1 divided by 1, 1 divided by 2, 1 divided by 3, 1 divided by 4, 1 divided by 5, and so on. And we have 2 divided by 1, 2 divided by 2, and we have these positive rationals where the numerator is 2, then we have 3 divided by things, and so on. So realize that this set of positive rationals, so the way we listed them, it goes off infinitely in many directions, in two-dimensional directions. But now here's a way of doing this. Say this is A1, this is the first element, this is the second element, third, and then keep on doing this by going through each diagonal. So do A1, A2, A3, then A4, A5, A6, A7, A8, A9, A10, and continue this. Go through each diagonal. We can certainly continue doing this because every diagonal is finite. So we are going to finish counting off each diagonal eventually. And in doing this, we are certainly going to contain every element of the positive rational. So we actually can get a sequence A1, A2, A3 such that every positive rational is in here somewhere. Now, what about negative rational? I mean, you can just do something similar. You can just arrange all the negative rationals. So you just put the negative signs here in a grid, and we do something similar to put them in a sequence, say B1, B2, B3, and so on. So it's possible to list all positive rationals in a sequence and all negative rationals in a sequence. And now how do I actually list all elements of Q? Well, to finish, all we have to do is the following. Just start with 0, which is listed in neither one of these sequences, and then just go back and forth between A and B. So A1, B1, A2, B2, and so on. And this is going to be a sequence in Q such that every element of the rational number is going to appear at least once in the sequence. So we indeed have that Q is countable. Now to top it all off, I claim that for the set of real numbers, this is not countable, it's uncountable. And this is a really fascinating fact due to Cantor. And if you've never seen this before, you're probably amazed. What I'm really saying here is that real numbers in some sense is a larger infinity than any of these sets. Even though integers and rational numbers do have infinitely many elements as well as R, these are small enough infinity in some sense that we can list all of their elements in a sequence, whereas we cannot do this for the real numbers. So let's try showing this. So the claim here is that if I try to list out all elements of real numbers in a sequence, then we actually cannot do that. If we consider any sequence in R, so if we consider any real sequence, then there is going to be a real number that's left out, that's not in the sequence. So to show this, let's just consider a sequence of real numbers. It can really be anything, but let me just make up some numbers. So maybe the first number in the sequence is maybe like 26.13151 and so on. Maybe the second number is 1 point something, maybe something like this. And maybe the next number is something like this. Maybe it's some large number, then we have a bunch of decimal digits. So maybe something like this, and then so on. So here we have a sequence of real number where this is the first element, this is the second element, this is the third element, and continuing. And now look at the first digit after the decimal point for the first number, the second digit after the decimal point for the second real number, and then the third digit after the decimal point for the third number. And so look at this diagonal and pluck off those numbers to get us a real number, say like 0.128 and so on. So all I'm doing here is I'm just looking at these digits and I'm turning them into a real number. And now here's what I'm going to do. For each digit in this real number, I'm going to change it. So change each digit. So you must change it, but you only change it to 1 or 2. So for example, for 0.128, for 1, I have to change the digit, but I can only change to 1 or 2, so I guess I must change it to 2. For the second digit, it's 2, so I can only change it to 1. For 8, we have some choice. We can either change it to 1 or 2. So let's say we change it to 1, and we continue this process, changing each digit to 1 or 2 to get some number here. And now, listen carefully, I claim that this number, this real number, is not part of the sequence. So what I'm saying is, if I have any sequence of real numbers, say A1, A2, A3, and so on, and we do this process to get some real number like this, then this real number is not going to be accounted for in the sequence. And that's telling us that we cannot have a sequence with every real number, so R has to be uncountable. So now you might ask, that sounds fascinating, but why is this number not on the list? Well, look at the first digit. We purposefully constructed this number such that this first digit is different from the first digit after the decimal point of the first number. So this first number on the list cannot be our number here because they differ in the first digit. Now let's look at the second digit. Well, the second digit, we constructed it, we chose it such that it's different from the second digit of the second number. And that's telling us that this number cannot be the same as this number. And we continue this process and we just rule out every number for each digit. So we see that this number is actually not on the list. Well, you might argue maybe it's actually on the list. Maybe the decimal expansion is not unique. So maybe in some different decimal expansion, we actually have this number in the list. But remember from one of the claims I made earlier that the only ambiguity in the uniqueness of decimal expansion occurs from repeating zeros or repeating nines. But this number, certainly, because it only has 1 or 2 as the digit, we cannot have repeating 0 or repeating nines here. So the decimal expansion of this number is unique. So the argument goes through. So that shows that R is uncountable, which is a fascinating fact. Okay, I think that's a good stopping place. In the next episode, we're going to actually see how we can use the list upper bound property of the real numbers and start talking about what's called a metric space.